Welcome back. Last episode, we ran the product rule backwards and got integration by parts. With substitution and parts in hand, you can already crack a huge fraction of the integrals you'll meet in a first calculus course. This time, we tackle the trigonometric corner of the universe, and there are really two stories. Story 1, the integrand is already full of sine and cosine, raised to various powers, and you need a strategy. Story 2, the integrand has no trig in it at all. It's something like the square root of 1 minus x squared, and yet trig is exactly the tool that finishes it, because you can introduce a trig function on purpose and use the Pythagorean identity to collapse the square root. So one episode, two faces of the same idea. Powers of sine and cosine first. Then trig substitution, with the integral of dx over the square root of 1 minus x squared giving us arcsine of x for free, and the integral of the square root of 4 minus x squared giving us the area of a semicircular segment with nothing but symbol pushing. Here's the first problem. You're asked to integrate sine to the m of x times cosine to the n of x, where m and n are non-negative integers. There's no formula in a table for general m and n. The product of mixed powers of sine and cosine just doesn't have a clean closed form you can look up. But it has a clean strategy, and the strategy uses exactly one fact, the Pythagorean identity, sine squared plus cosine squared equals 1. That identity lets you trade. Anywhere you see sine squared of x, you can replace it with 1 minus cosine squared of x. Anywhere you see cosine squared of x, replace with 1 minus sine squared of x. The plan, in one sentence, get the integrand into the form of a polynomial in sine of x times a single cosine of x, or a polynomial in cosine of x times a single sine of x. Then substitute u equals sine of x or u equals cosine of x. The lone trig factor is exactly the du you need. The integrand becomes a polynomial in u, which you integrate by brute force. The art is in the parity. Which one's odd? That's the one you peel a factor off and convert. 3 cases, organized by parity. Case 1, m is odd. The power of sine is odd. Then peel off 1 sine of x and set it aside. That'll be our du. What's left is sine to the m minus 1 of x, which has even power, so I can rewrite it using sine squared equals 1 minus cosine squared, turn every sine squared into 1 minus cosine squared. Now everything except the peeled off sine of x is in terms of cosine of x. Substitute u equals cosine of x, du equals negative sine of x dx. The peeled sine of x dx becomes negative du. The rest is a polynomial in u. Done. Case 2, n is odd. Mirror image. Peel 1 cosine of x, convert the rest with cosine squared equals 1 minus sine squared, substitute u equals sine of x. Case 3, both m and n are even. Now there's no odd factor to peel. Both powers are even, so neither sine of x dx nor cosine of x dx shows up cleanly. Here you use power reduction, sine squared of x equals 1 minus cosine of 2x over 2, cosine squared of x equals 1 plus cosine of 2x over 2. Each application of a power reduction formula trades an even power of sine or cosine for a first power of cosine of 2x at a constant. That's a simpler integrand. If you still have squares left, apply again. Iterate until the powers are down to 1. 3 cases, fully systematic. Parity tells you which one you're in. Concrete example. Compute the integral of sine cubed of x times cosine squared of x dx. Parity check. The power of sine is 3, odd. We're in case 1. Peel off 1 sine of x to be the du and rewrite the remaining sine squared of x as 1 minus cosine squared of x. So the integrand becomes the quantity 1 minus cosine squared of x times cosine squared of x times sine of x. Now substitute. Let u equal cosine of x. Then du equals negative sine of x dx, which means sine of x dx equals negative du. Everything in the integrand that isn't the peeled off sine of x dx is in terms of cosine of x, which becomes u. The integral transforms into the integral of the quantity 1 minus u squared times negative du. Pull the minus sign out, expand, negative, the integral of the quantity u squared minus u to the 4th du. Distribute the minus, the integral of the quantity u to the 4th minus u squared du. Wait, let me be careful. The minus stays outside, negative the quantity u cubed over 3 minus u to the 5th over 5 plus c, which equals u to the 5th over 5 minus u cubed over 3 plus c. Back substitute u equals cosine of x. The final answer is cosine to the 5th of x over 5 minus cosine cubed of x over 3, plus the constant. Check by differentiating if you want. Product rule plus chain rule, and the original sine cubed of x times cosine squared of x drops out. The whole computation was identify the odd power, peel, convert, substitute, polynomial integrate. 5 lines. Now the deeper trick. Suppose the integrand has no trig in it whatsoever. It has, instead, a square root of a quadratic. Specifically, one of 3 shapes, the square root of a squared minus x squared, the square root of a squared plus x squared, or the square root of x squared minus a squared, a constant minus x squared, a constant plus x squared, or x squared minus a constant, all under a square root. You can't easily integrate things like that with u substitution or parts. The square root resists. Here's the move. Introduce a trig function. Set x equal to a sine theta, or a tangent theta, or a secant theta, depending on the shape. Why? Because of the Pythagorean identities. Sine squared plus cosine squared equals 1 rearranges to 1 minus sine squared equals cosine squared. Multiply through by a squared and you get a squared minus a squared sine squared theta equals a squared cosine squared theta. Take a square root. The square root of a squared minus a squared sine squared theta equals a cosine theta. The radical disappears, replaced by a clean trig function. Same trick with tangent squared plus 1 equals secant squared. Multiply by a squared tangent squared plus a squared equals a squared secant squared, so the square root of a squared plus a squared tangent squared theta equals a secant theta. And secant squared minus 1 equals tangent squared gives the square root of a squared secant squared theta minus a squared equals a tangent theta. Pick the right substitution for the shape, and the square root is annihilated by an identity. That's the whole idea of trig sub. One practical note before we work examples. After a trig sub, you'll get an answer in terms of theta. But the original problem was in terms of x, so you need to translate back. And the cleanest tool for that is a reference triangle. Take the substitution x equals a sine theta. That says sine theta equals x over a. So draw a right triangle where sine theta, opposite over hypotenuse, is x over a. The hypotenuse is a. The side opposite theta is x. By the Pythagorean theorem, the third side, adjacent to theta, is the square root of a squared minus x squared. With that triangle drawn, you can read off every trig function of theta directly in terms of x and a. Sine theta equals x over a. Cosine theta equals the square root of a squared minus x squared over a. Tangent theta equals x over the square root of a squared minus x squared, and so on. Whatever shows up in your antiderivative, the triangle tells you what it is back in terms of x. Same trick works for the other two substitutions. Draw the triangle, label the sides, read off the conversion. We'll lean on this when we finish the integral of the square root of 4 minus x squared example. First example, the absolute simplest possible. Compute the integral of dx over the square root of 1 minus x squared. The radical is the square root of 1 minus x squared. That's the square root of a squared minus x squared shape with a equals 1. So substitute x equals sine theta. Then dx equals cosine theta, d theta. Plug everything in. The radical, the square root of 1 minus x squared, becomes the square root of 1 minus sine squared theta, which by the Pythagorean identity is the square root of cosine squared theta, which is cosine theta. The square root has collapsed to one trig function. That's the entire point of trig sub. Now the integrand. Numerator, dx equals cosine theta d theta. Denominator, cosine theta. The cosines cancel exactly. We're left with the integral of 1 d theta, which is just theta plus c. Back substitute. X equals sine theta means theta equals arcsine of x, so the integral equals arcsine of x plus c. And there's our sanity check, which doubles as one of the most used antiderivatives in calculus. The derivative of arcsine of x is 1 over the square root of 1 minus x squared. Integrating, going the other way, gives back arcsine of x. Trig sub just derived that with no appeal to the inverse function rule. The square root vanished under the identity, the integral became trivial, and arcsine fell out as the answer. Second example, the showpiece. Compute the integral of the square root of 4 minus x squared dx. Before any algebra, what does this integral mean? The graph of y equals the square root of 4 minus x squared is the top half of the circle x squared plus y squared equals 4, a semicircle of radius 2. So when you integrate the square root of 4 minus x squared, you're computing the area under that semicircle. The full semicircle from -2 to 2 has area 2 pi, half of pi r squared with r equals 2, so any indefinite antiderivative we get had better, when plugged in at the endpoints, give us 2 pi. Right, to the calculus. The shape under the radical is the square root of a squared minus x squared with a equals 2, so substitute x equals 2 sine theta, giving dx equals 2 cosine theta d theta. Simplify the radical. The square root of 4 minus x squared equals the square root of 4 minus 4 sine squared theta equals the square root of 4 times the quantity 1 minus sine squared theta equals the square root of 4 cosine squared theta equals 2 cosine theta. The Pythagorean identity does it again. The radical goes away. We're ready to plug in. Plug in. The integrand, the square root of 4 minus x squared, becomes 2 cosine theta. The dx becomes 2 cosine theta d theta. Multiplied together, that's 4 cosine squared theta d theta. Pull the 4 out front. We're now computing 4 times the integral of cosine squared theta d theta. And look, We are back in the trig integrals world from the first half of this episode. We've turned a square root integral into a powers of cosine integral. The sine power is 0, the cosine power is 2, both even. That's case 3. Power reduction. Cosine squared theta equals 1 plus cosine of 2 theta over 2. So 4 cosine squared theta equals 2 times the quantity, 1 plus cosine of 2 theta, and the integral becomes 2 times the integral of the quantity 1 plus cosine of 2 theta d theta. Wait, let me redo the arithmetic. 4 times 1/2 is 2. So 4 times the integral of cosine squared theta d theta equals 2 times the integral of the quantity 1 plus cosine of 2 theta d theta. That's 2 theta plus sine of 2 theta plus c. The integral of cosine of 2 theta is sine of 2 theta over 2, and the 2 out front cancels the half. Clean. Almost done. One more cosmetic step. Rewrite sine of 2 theta using the double angle identity as 2 sine theta cosine theta. So the antiderivative, still in theta, is 2 theta plus 2 sine theta cosine theta plus c. Now, back, substitute. We have an answer in theta, but we need x. Draw the reference triangle for x equals 2 sine theta. Sine theta equals x over 2, hypotenuse 2, opposite side x, adjacent side, the square root of 4 minus x squared. So cosine theta equals adjacent over hypotenuse, the square root of 4 minus x squared over 2. And theta itself is arcsine of x over 2. Substitute these into 2 theta plus 2 sine theta cosine theta plus c. First term, 2 theta equals 2 arcsine of x over 2. Second term, 2 sine theta cosine theta equals 2 times x over 2 times the square root of 4 minus x squared over 2, which equals x over 2 times the square root of 4 minus x squared. Add the constant. Final answer, 2 arcsine of x over 2 plus x over 2 times the square root of 4 minus x squared plus c. And here's the most satisfying check in this whole episode. Plug in the bounds x equals -2 and x equals 2, which should give us the area of the full semicircle 2 pi. At x equals 2, 2 arcsine of 1 equals 2 times pi over 2 equals pi, plus 2 over 2 times 0 equals 0. Total, pi. At x equals -2, 2 arcsine of -1 equals -pi plus 0. Total, -pi. Subtract pi minus -pi equals 2 pi. The area of a semicircle of radius 2. We just computed geometry with pure symbol pushing. No diagram needed for the proof. Briefly, the other two. They follow the exact same pattern, only the identity changes. For the square root of a squared plus x squared sum instead of difference, let x equal a tangent theta. Then a squared plus x squared becomes a squared plus a squared tangent squared theta, which factors as a squared times the quantity 1 plus tangent squared theta. And 1 plus tangent squared equals secant squared is the Pythagorean identity in a different rearrangement. So a squared plus x squared equals a squared secant squared theta, and the square root is a secant theta. The differential, dx equals a secant squared theta d theta. After plugging in, you'll typically get an integral involving secant theta. Those have their own tricks, but everything reduces to standard antiderivatives. For the square root of x squared minus x squared minus a constant, let x equal a secant theta. Then x squared minus a squared equals a squared secant squared theta minus a squared equals a squared times the quantity secant squared theta minus 1 equals a squared tangent squared theta. So the square root of x squared minus a squared equals a tangent theta. And dx equals a secant theta tangent theta d theta. 3 substitutions, 3 Pythagorean identities, 3 radicals neutralized. Always end with a reference triangle to translate theta back to x. The pattern is the same every time. A bit of history. The Pythagorean identity itself, sine squared plus cosine squared equals 1, and the angle sum formulas are ancient. They show up in trigonometric tables compiled for astronomy by Hipparchus and Ptolemy in the Greek world 2,000 years ago, and in the work of Aryabhata, Brahmagupta, and Madhava in India through the medieval period. Madhava in particular, in Kerala in the 1300s and 1400s, was computing series for sine and arctangent, essentially Taylor series, 3 centuries before Newton and Leibniz. The trig identities were the most heavily used tools in pre-modern mathematics, but integration as a formal subject is from Newton and Leibniz in the late 1600s. Trig substitution as a systematic technique, the move of introducing a trig function into a non-trig integral, really crystallized in the 1700s. Euler is the central figure. His Institutiones Calculi Integralis, published 1768 through 1770, is a multi-volume treatise that cataloged every integration technique then known and essentially defined the curriculum that's still taught. Euler's mastery of trig identities and trig substitution is unmatched. The clean reference triangle presentation we use today, the picture-driven version, was refined in 19th century textbooks by Cauchy, Lacroix, and others working in the tradition of teaching calculus to engineers. So the identity is ancient, the integration trick is Enlightenment, the pedagogy is 19th century. 4 practical notes. First, When you take the square root of cosine squared theta, that's technically the absolute value of cosine theta, not just cosine theta. We almost always drop the absolute value silently. We can do that because the standard theta range for the sign substitution is negative pi over 2 to pi over 2, on which cosine is non-negative. Similarly for the other subs, choose the right theta interval and the absolute values disappear. The textbooks rarely mention this, but it's why the calculation works. Second, for definite integrals you have two ways. Either compute the indefinite antiderivative, back substitute to x, and evaluate at the original bounds. Or transform the bounds when you substitute. If x goes from 0 to 2 and x equals 2 sine theta, then theta goes from 0 to pi over 2 and skip back, substitution entirely. Pick whichever is cleaner for your problem. Third, for powers of sine and cosine where both are odd you have a choice, peel a sine or peel a cosine. Pick the one with the smaller exponent, less conversion, less algebra. Fourth, if you see a radical like the square root of x squared plus 4x plus 1 that's not in standard form yet, complete the square to turn it into the square root of the quantity x plus 2 squared minus 3. Now a shift u equals x plus 2 puts it in the square root of u squared minus 3 shape, and trig sub kicks in. Completing the square is the unsung step that lets trig sub handle any quadratic under a radical. Recap. Trig integrals. Mixed powers of sine and cosine are handled by parity. If a power is odd, peel one factor to be the du, convert the rest using sine squared equals 1 minus cosine squared, and substitute. The integrand turns into a polynomial, integrate term by term. If both powers are even, use the power reduction formulas to halve the exponents and iterate. Worked example, the integral of sine cubed of x times cosine squared of x dx equals cosine to the fifth of x over 5 minus cosine cubed of x over 3 plus c trig substitution. When a radical of a quadratic shows up, the square root of a squared minus x squared, the square root of a squared plus x squared, or the square root of x squared minus a squared, introduce a trig function so a Pythagorean identity collapses the square root. The three subs, a sine theta, a tangent theta, a secant theta respectively. Worked examples. The integral of dx over the square root of 1 minus x squared equals arcsine of x plus c, and trig sub just derived that, no inverse function rule required. And the integral of the square root of 4 minus x squared dx equals 2 arcsine of x over 2 plus x over 2 times the square root of 4 minus x squared plus c, which is the area under a semicircle of radius 2, geometry from pure algebra. Always finish with a reference triangle to translate theta back to x. The triangle does the bookkeeping. Next episode, partial fractions. Rational functions decompose into pieces you already know how to integrate, and there's a beautiful algebraic procedure for finding the decomposition. With partial fractions added to substitution, parts, and trig sub, you'll have the entire Calculus 2 toolkit. See you there. That's trig integrals and trig substitution. If this was helpful, hit like, leave a comment, and consider subscribing. It really does help the channel reach more learners. Post your favorite trig sub problem in the comments. Bonus points if it requires completing the square first, or if it sneaks in an integral that looks algebraic but turns out to be a semicircle in disguise. Next episode, partial fractions decomposition. We'll take rational functions, quotients of polynomials, and tear them apart into pieces small enough that each one is a one-line integral. With that, you'll have seen the full standard Calculus 2 integration toolkit. See you in the next one. 3 big techniques down: substitution, parts, trig sub. One major family left in the standard Calculus 2 toolkit, partial fractions. The setup, you have a rational function, p of xq of x, and even though it's an algebraic beast, every such function decomposes into a sum of pieces you already know how to integrate. 1tx minus a, 1tx minus a to the k, and 1tx squared plus bx plus c. Find the decomposition, integrate termwise, done. Next episode, I'll show you the cover-up method, the systematic linear algebra approach, and why this technique secretly underlies Laplace transforms. Subscribe, see you there. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.